record. Shoot, I can't believe I forgot that. And then we'll be covering 3 other lines of evidence in future lectures. Then we'll be talking about everybody's favorite subjects, galactic collisions, when galaxies collide, and in particular, when the Andromeda Galaxy collides with us. Will it destroy us? So refresh your memory. Hubble's law said that the speed that something was receding from us increases the farther away it is from us, and that's codified with Hubble's law. The recession velocity away from us is directly proportional to the distance away from us times the Hubble constant. And this is consistent with the entire universe expanding uniformly. And because the entire universe is expanding uniformly, if we wind that clock back, that means at some point in time, the universe must have been a point. In other words, our universe had a beginning. And so this Hubble expansion graph was not only a scientific graph, but a philosophical graph, stating the universe had a beginning. And later on, we'll discover that the universe has an end. Okay, so this recession velocity is calculated from the redshift, which uses the same equations, but is not a velocity redshift, but is a redshift over the expansion of space itself. And we use to calculate distances in the galaxy, and using those distances to calculate the shape and the size and the history of the universe, we use a distance ladder. And the distance ladder is for closest things. We use this laser ranging, Kepler's laws. For nearby stars, we use parallax. For distant clusters, we use the fact that if you're on the main sequence, you have a very specific relationship between your color, your temperature, and your absolute luminosity, which will tell you what your distance is. For nearby galaxies, we can use Cepheid variables, which oscillate at a specific frequency based on their absolute luminosity. And for very distant galaxies, we can use type 1a supernova because they always explode at the same luminosity. So start with a question here. How could we get the distances to the nearest galaxies a few megaparsecs? So A, by parallax, B, by the period luminosity relation for Cepheids, C, Hubble's law, D, radar reflection, E, mate sequence fitting. And remember, there's no right or, well, you're not graded on these questions. Okay, so most of you chose Hubble's law. And I suppose you could use Hubble's law to the nearest galaxies, but you wouldn't want to. And the reason you wouldn't want to is because when you're talking about galaxies that are near to us, they're so close that they have significant velocities that peculiar velocities that are actually larger than the expansion velocity, the cosmological velocity. And so it's just not a good measure. What is a good measure is using Cepheids. Cepheids will go out to certainly approach the nearest galaxies. So the correct answer for this one is actually B. You really only use Hubble's law when you're talking about very, very distant galaxies where the recession velocity is very large, much larger than the peculiar velocity, because galaxies are moving around each other all the time. So going back to that, you see a distant car at night. This is actually a great question. So you see a distant car at night. What 2 things must you know in order to estimate its distance? A, how fast it's moving towards or away from you. B, the apparent brightness of the distant headlines. C, the intrinsic brightness of the headlines. Okay, interesting. So most of you chose D, which is A and B, how fast it's moving in the apparent brightness. So let's annotate text. Okay, so I want you to remember that the brightness of an object is equal to the intrinsic luminosity of the object, how bright it really is. So brightness is how bright it appears. Luminosity is its intrinsic brightness, how bright, how much energy it generates, divided by the distance squared. Okay, and let's ask this question again. Okay, so now most of you chose E, which is correct. E is based on the apparent brightness and the intrinsic brightness. I can calculate the distance. So if you know the intrinsic brightness and the apparent brightness is easy. That's how bright it appears in the night sky. The intrinsic brightness you usually don't know, but in the case of supernova, type 1 supernova, you do know because you know they all reach the same maximum brightness. And notice that neither of these involve the speed, okay? It was only Hubble that was able to relate through the Hubble relation that there was a relationship between speed and distance. But that's the Hubble relation, not this intrinsic brightness. This is known physics that is just fundamental. I mean, this is one of the fundamental laws of physics, that the brightness of something varies as the intrinsic luminosity over r squared. And you can observe this every night you go out. Flashlights are bright if they're close, and they're dim if they're far away. You don't know whether it's just a really bright flashlight or a really close flashlight. I mean, you can observe this every day of your lives. Um, the Hubble relationship is an observation that isn't related to this. It's an observation that the universe must be expanding because there is a relationship between the expansion velocity uh, and how far away things are. And you could imagine a universe, and certainly people did, where that is not true. And that would be a static universe that isn't expanding. So the Hubble relationship is not a fundamental basic law of physics. It was an observation that the universe is expanding. Okay, so let's annotate, clear all, and how do I stop this? There we go. And we do this through the standard candle. This is exactly what I said, that the standard candle, as we talked about last time and we just talked about, is if you know the intrinsic brightness of something and you know how bright it appears, you can calculate how far away it is. Okay, so let's do another one. You see a distant main sequence B-type star in Rigel in a rather distant galaxy. What two things do you need to know in order to estimate its distance? So it's a main sequence B star. You need to know A, how fast it's moving towards or away from you, B, its apparent brightness, C, the intrinsic brightness of main sequence B-type stars like Rigel. Okay. So there's some confusion here. Let's go over this again. Remember, the brightness, what is the apparent brightness, B, is equal to the intrinsic brightness, L, over the distance squared, okay? So this is an equation of 3 variables. If you know 2 of the variables, you can calculate the third. So if you know the radius, the distance r, and the intrinsic brightness L, then you can calculate what its brightness is, B. If you know its brightness B, and you know its distance r, then you can calculate what its intrinsic brightness is, L, and through any combination of that. So let us relaunch this. Okay, so that works. So now you can see that the correct answer is E. You need to know both the apparent brightness and the intrinsic brightness. You need to know B and L. If you know B and L, then you can calculate what the distances are. Okay. So let's get rid of this, clear, and stop annotating. And so there's Rigel. If it's on the main sequence, and we will know exactly what its luminosity is because the main sequence is relatively narrow. If you know the temperature of a star on the main sequence, you know its luminosity. Just go up there and then go over there. Let's skip this question. And remember, type 1a supernova, B equals L over R squared. You know what L is. You know its intrinsic brightness because all type 1 supernovas are exactly the same. They always blow up when they reach 1.4 solar masses, and the entire star blows up. All of the carbon in the white dwarf blows up at the same time. Okay. So that's all reviewed. Now let's talk about what dark matter is. The first evidence for dark matter came about in the 1930s. And when this evidence came about, people thought that there must be something wrong with their instruments, and they really didn't think about it again until the 1970s, when I think it was Vera Rubin who really looked into us in this excruciating detail. The problem is that we were looking at the rotation speeds of stars around the center of our galaxy. And these dots here map what that rotation velocity is. Okay, so dot, 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 dot. That's the data. The red is a purported fit of that. The problem is this blue dotted line here is the line that they should have observed. And this is the line we do observe in our solar system, where Mercury orbits very rapidly around the sun, and you get down here and Pluto orbits very slowly around the sun. So we would have expected that the farther out you get in the disk, the slower the stars are going as they rotate around the center of the Milky Way galaxy. And that's assuming, based on observations, that the vast majority of the mass of the galaxy is concentrated in the central bulge here, okay? And certainly that is where the vast majority of stars are. And so this observation that even far out on the disk, these stars were still rotating really fast implied that the assumption that all of the mass of the galaxy was concentrated in the center, as it is in the solar system, and actually in all solar systems, had to be incorrect, that there had to be masses other than at the center. So here, the velocity of anything that's orbiting a thing goes as the square root of the mass that's enclosed over the radius of that. So this is actually a square root of 1 over r curve, okay? And so what this means is, as you go farther out, it must be enclosing more and more mass. In other words, there was more mass in the disk than you could see. There was more mass in the disk than you can account for by counting the stars and also counting all the gas and dust you saw. So there had to be more mass than you could see, and hence the term dark matter. There had to be matter that was affecting these stars gravitationally, and you couldn't see it. Um, and so this term, people started taking this seriously in the 1970s, and it wasn't until more recently, in say the last 20 years, we have so many lines of evidence that the evidence for dark matter is so overwhelming, it is now considered a fact. The vast majority of matter in the universe is dark matter that we don't know anything about. And let's compare dark matter to the Force. Well, the Force is what gives a Jedi his power. It's an energy field created by all living things. It surrounds us and penetrates us. It binds the galaxy together. Well, dark matter doesn't give a Jedi his power. We don't believe. And is it an energy field? We don't know. We don't know what it is. We don't know if it's a field, if it's a particle. We just don't know. It's certainly not created by all living things. However, dark matter does surround us. It does penetrate us. Your body is being swamped by dark matter continuously right now. And it most definitely binds the universe together. Without dark matter, our universe would not hold together. Okay. So when you see Star Wars and they talk about the Force, think dark matter. Okay. So ordinary matter versus dark matter. Ordinary matter, it has mass. It consists of stars, galaxies, planets, dust, rocks, anything we can see, anything we can measure. And we usually detect it through electromagnetic radiation. And until 2015, that was the only way we could detect it, was through electromagnetic radiation. And that means that ordinary matter interacts with electromagnetic radiation. It absorbs it, it reflects it, it emits it. Okay, so normal matter and electromagnetic radiation love each other. They have this dance. One creates the other. Uh, uh, Electromagnetic radiation is emitted by normal matter, and normal matter will also absorb electromagnetic radiation. Okay, so they are intimately involved with each other. Dark matter, on the other hand, is a different sort of animal. It has mass. Okay. If it didn't have mass, we couldn't observe it the way we do. So we observe it through its gravitational interactions. But as far as we know, it doesn't interact with electromagnetism in any way. Light passes right through it. Radio waves, X rays, gamma rays, ultraviolet, whatever, all of it passes right through as if it didn't exist. And this is so contrary to our perceptions that it's just taken a while for us to realize what the ramifications are. And not only that, but current estimates are there's 10 times more dark matter than there is ordinary matter. So the vast majority of gravitationally massive stuff in the universe is stuff that does not interact with electromagnetism. We can't see it. It permeates space, but we can't see it. We can't observe it. And we can detect it only indirectly by its gravitational interactions. And it's 85%, 85 to 90% of the matter in the universe. Here's a short video.
Have you ever had the feeling that there's something bigger out there, something you can't see? Well, there is. It's called dark matter. Dark matter is spread throughout space, engulfing the Milky Way and all other galaxies. It's 4 times more common in the universe than visible matter, yet we've never seen or directly observed it. So how do we know it's there? Because of gravity. A galaxy is like a giant merry-go-round that all the stars are riding. In order to stay on, each star has to hold on tight. That's where gravity comes in. Otherwise, it'll fly off into space. The problem is, the force of gravity from all the stars we can see isn't strong enough to hold galaxies together. All the stars should be flying off the edge of the merry-go-round, but they're not. It's as if some invisible rope is helping them hold on. Physicists believe that rope is the gravitational force from stuff we can't see, hence dark matter. And how do we know the speeds of stars in distant galaxies? The Doppler effect, which is why a police siren shifts to a lower pitch as the car passes, also works for light. That's how radar catches you speeding, and how astronomers measure the rotation of galaxies. So, we use what we can see to tell us about what we can't.
Okay. And we'll have more videos coming up. So we have 4 lines of evidence for dark matter that we'll be talking about today, and then we have 3 other lines we'll be talking about in future lectures. We've just talked about the galactic rotation curves, and here's a little bit more detail about that. So if you rotate a disk, okay, the velocity of the rotation will increase linearly. In other words, the edge of your frisbee, as it's rotating, is going to spin a lot faster than the inner part of the frisbee that's spinning, okay? A planetary, what we call Keplerian rotation, where the planets that are close to the sun are going to be rotating very fast. The planets farther away are going to be rotating slower. And this is exactly what we observe in our solar system and in all other solar systems. And here is our solar system. The inner planets have very fast velocity. The outer planets have very slow velocities. Okay? And here is the curve for the solar system. It matches the Keplerian curve exactly as you would expect. And here is what we've observed with the galaxy, with the Milky Way galaxy. It doesn't match either of these curves. It does something bizarre. The rotation curve is approximately constant, which means as you get farther away from the center of the galaxy, you're enclosing more and more mass that you cannot see. So on the left is what we should see. Here is the rotation of the objects at the outer reaches should be going very, very slowly. Here is the rotation we actually observe. The outer stars are moving much faster than they should. Okay. Which means that the mass that's enclosed must increase as you come out farther in radius. The only way this can work is if surrounding our galaxy is what we call a black matter, a dark matter halo, okay? That there's dark matter that extends way beyond the reaches of the visible Milky Way galaxy itself. And we can observe these as you talked about using we can observe this not only in the Milky Way galaxy, but in virtually every other galaxy. If we look at individual slices of these other galaxies, we can see they have exactly the same rotation curve. The implication is all galaxies have these dark matter halos that contain 10 times more matter than the galaxy itself. The northern precincts appear red, which means they're moving away from us, whereas the blue regions are approaching us. I believe this district may be rotating in space. Anyway, sorry. I thought that was cute. So that's number 1. Number 2 is galaxy clusters. We observe the velocities of galaxies, and galaxies, they're just rife. In fact, let me just show you galaxies. Stars are very far away from each other. So our star takes, a couple of light seconds to go across the diameter of the star of our sun. And the closest star to our sun is 4 light years away. So that's seconds versus years. That's a factor of 10 million. With galaxies, if you look at the ratio of the size of the galaxy to the distance to other galaxies, it's typically 10 to 1, not 10 million, but 10. So let me show you that. Okay, so here is the Milky Way galaxy, and here are galaxies. There's the Andromeda galaxy. Here's other galaxies that are close to us. So galaxies tend to be very close together. In fact, later we'll talk about how the Andromeda galaxy is going to be approaching us in a few billion years. Okay, stop that. New share. So what we observe is these galaxies definitely form a cluster. They're all clustered together, and in fact, the cluster that we're part of is called the local group. But they tend to be moving much faster in this cluster than would be expected if you counted up all the mass based on all the stars and gas and dust in each of those galaxies. In fact, they're moving so fast that if something wasn't binding them together, the cluster should not exist, that all of these galaxies should have spun off away from each other a long time ago. But these galaxy clusters persist, and they persist because there must be a lot more mass in the cluster than we can see. And that mass, of course, is dark matter. And it's 10 times more dark matter than what you can see. And the second line of evidence is the fact that galactic clusters exist and they don't evaporate instantly. That's evidence number 2. Evidence number 3, I'm going to go over this in some detail. This is an observation that came out about 10 years ago, and it's of a single observation of 2 galaxies that have collided. And here is the picture, and it's a little confusing. What the red represents is when 2 galaxies collide, their gas clouds collide. And when those gas clouds collide, not only do they form new stars, but they glow, they become very hot and they glow in X-rays. And so the red here represents the X-rays that are being emitted from the collision of these 2 galaxies. The blue represents the mapping of the masses of these 2 galaxies that collided. And we were able to map the masses of these 2 galaxies by using gravitational lensing, which we'll be talking about in a couple of minutes. Okay. So here, the red represents the gas and dust of the collision, and the blue represents the mass of the galaxies. And here's what we would expect happen in regular matter. If you have 2 things that slam into each other, so you run into your best friend or your worst enemy, doesn't matter. And what happens is both of you slam into each other and you stop. Okay. And if you run towards each other really hard, then you create this ball of humanity. Okay. Dark matter. Dark matter doesn't interact with electromagnetism. And as far as we know, it actually doesn't even interact with itself. And so you have 2 lumps of dark matter. What happens is they pass through each other. Okay. So that was the theory. And what's called the bullet cluster, we ran this simulation where if you had 2 galaxies that slammed into each other, what would happen is the normal matter represented by that gas and dust would slow down because of that collision. It would slow down and heat up. But the dark matter would continue on as if nothing happened. And that is exactly what we observed. Let me run that simulation again. Here we have the 2 galaxies, they slam into each other. The gas and dust heats up and slows down, and that's represented by the red. But the masses, the dark matter, is completely unaffected. And that's exactly what we see. Okay. There's the X-rays, and there is the dark matter, or the mapping of the mass, which is mostly dark matter. Okay, so this was when this evidence came out, was it 10, 15 years ago? This was kind of the nail in the coffin of alternate theories for dark matter. We basically proved that we have observed that dark matter exists and dark matter does not interact even with itself. Line of evidence number 3. Line of evidence number 4 is a prediction that Einstein made, and then he also predicted that this would never be observed, was what we know as gravitational lensing. In normal lensing, as we covered when we talked about telescopes, light is bent as it refracts through lenses where the speed of light is less than the speed of light. But there's other ways of bending light. One of the ways of bending light is just through mass. As we talked about, when you have something that's extremely massive, it warps space-time, and that warping of space-time will affect the flight of your rocket ship past the massive object, but it will also affect the passage of light. And so you can use mass to create lenses just like optical lenses, except you're using gravity to do so. So here we have a piece of mass, and as you can see, its path is bent because of the warping of space-time caused by density mass. And here that warping of space-time also causes light to bend, okay? And this is called gravitational lensing. So let's go to I used to live outside Baltimore, and here is a black hole visiting Baltimore.
This scientific visualization demonstrates the visual distortion known as gravitational lensing. A black hole with roughly the mass of Saturn is imagined to pass over the inner harbor in Baltimore, Maryland. The view of the buildings on the far side of the harbor are distorted using the calculated effects of Einstein's general relativity. A black hole warps the space around it. Light that passes near a black hole will follow curved paths and can create multiple images and other visual artifacts. Note that the sky can sometimes be seen by looking below the black hole. These distortions are similar to what can be produced using glass lenses and are produced by similar optics equations. The effects are called gravitational lensing, lensing that redirects light using mass instead of glass.
I love that. Using mass instead of glass. Okay, so I'm going to show you another simulation. And what the simulation shows is what we would expect from the cluster if the cluster contains mostly dark matter. And then we remove the dark matter, and you can see how the gravitational lensing changes. Oh, I'm sorry. First, we're going to show you some images of this sort of gravitational lensing. And as you can see, as you saw through the images of the trip through Baltimore, the warping of light as it goes around a massive object is it uses the same equations as optics, but the images are kind of trippy, as James said. No, I'm sorry, Andrew said. And you can see here, these are called Einstein's rings. And there is a galaxy, this blue galaxy, which is behind this galaxy here. And so this entire galaxy is the gravitational lens that forms this image of the background galaxy, and it's warped into these rings. Okay, just as you saw in that simulation as we went through Baltimore. Okay, so Einstein didn't think that we would ever be able to see the effects of gravitational lensing, but in fact, we see it all over the place. I mean, literally all over the place. There's millions and millions of examples like these. Some subtle, but these are not so subtle. The subtle ones would be like these here. You can see even far away, you've got a warping of the images of those galaxies. Okay. And here we've got this warping around here. So lots and lots of gravitational lensing. And through this gravitational lensing, we can map the amount of mass between us and the background galaxies. And when we map the amount of mass that's needed to produce these images, it's 10 times more than we can see. Okay. And here's the sequence I was talking about. At first, we're going to see a simulation of what the star field should look like, assuming that a certain galactic cluster has the amount of mass that we know exists, which would the mass that we can see plus the dark matter that would exist in that cluster. And then halfway through the simulation, we remove all of the dark matter. So here you can see the warping of the images of the star field as the light passes through this galactic cluster, which is represented by the yellow stars there. And then halfway through, we just remove all of the dark matter and see what happens. And all of a sudden, you don't see, not only does the galactic cluster explode, but you don't see that sort of warping that you do, okay, when you have so much dark matter. So those are the 4 lines of evidence. Galactic rotation curve, 3 to 10 times the mass of the galaxy would have to be outside the visible part to reproduce the observed curve. The galactic galaxy clusters are moving much too fast to exist if they didn't have dark matter to bind them together. The bullet cluster, the ordinary matter and dark matter don't line up after the collision. The ordinary matter is slowed down. The dark matter is not slowed down. That's line of evidence number 3. Line of evidence number 4 is there's way, way more gravitational lensing than we would expect if the only matter that existed is matter we could see. Okay. Line evidence number 5 has to do with Big Bang nucleosynthesis, the creation of elements during the Big Bang. We'll be talking about that in a future lecture. Line evidence number 6 is the cosmic microwave background. The fact that it is not uniform is basically another nail in the coffin that dark matter must exist or we wouldn't be here. And line evidence number 7 is the fact that the structure of the universe on very large scales looks like a bunch of spider webs, and that only happens if you run your simulations with a certain amount of dark matter. Now, these numbers, 4% or normal matter in the universe, 23% dark matter, and then 73% dark energy, which we'll cover in a future lecture, is just one. These numbers bounce around quite a bit, and I don't even think these are current canonical numbers, but basically, most people are talking about 5 to 10 times more dark matter than ordinary matter, and dark matter and ordinary matter added up together is only a 1/4 of the universe. The rest of the universe is dark energy, which we'll cover in a future lecture. Dark matter, dark energy are labels for our ignorance. They told us starting in 1999 that we knew nothing, Jon Snow, that we thought we knew the universe, and it turns out we don't. Okay. And here's a cute video. This was a student project, just like the ones you guys will be doing, although it wasn't at this university.
No Skills Entertainment. Space stuff. Dark matter.
Look up in the sky, there's the moon you see. There's some stars, there goes Mars, Pluto, RIP. Those are just a few of the things in our galaxy. All of it's held together by tons of gravity. But what if gravity wasn't strong enough? Everything in the universe is held by some other stuff. Some other stuff you cannot see with the naked eye. Some other stuff that doesn't shine when it's hit with light. It seems that we have ourselves another mystery. So let's travel back in time to 1933. Fritz Zwicky was observing the coma clusters, and this would lead to an astronomy adjuster. He was measuring those galaxies' mass, and based on the observed mass, they were moving way too fast. There had to be something else to cause such speeds. Apparently, we have missing matter missing from the galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. The center of our solar system is the sun. The closer that you get to it, the stronger gravity becomes. Close planets revolve fast, far planets slow. It's the gravity to distance to speed ratio. So if the coma clusters are moving too rapidly, maybe something invisible added to its gravity. Decades later, based on further observations, dark matter is the name of the situation. Well, what is it? No one knows for sure. An accurate description remains unsecured. Search for answers activated, simple yet complicated, constantly investigated, mysteries generated. Matter or a particle, guesses hypothetical, research problematical, and others very skeptical. But for now, that's just how the story goes. It's a known unknown, a thing we know but just don't know. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. There's a lot of concern with the dark matter case, as it may be 80% of the stuff in space.
That's a lot.
Holding the stars together like some cosmic pace. Scientists are in a rush of proof. Space race. Let's talk about some of the theories that have generated dark matter, maybe how our universe originated. Following the Big Bang, the universe formed after, and it may have come together with the help of dark matter. String theory mentions dimensional planes, stacked on top of each other like some video games. There's universes above us, but we cannot see them. Dark matter may be the gravity that's in between them. So if you're in a quest for the dark matter reward, you'll have to explore 11 dimensions or even more. Now I understand if that is hard to believe. The universe is like bread and dark matter is the cheese. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see. Or maybe we just don't understand gravity.
Maybe you're right about that.
Yeah, we actually don't understand it. We thought we did, but we don't. So that's the evidence for dark matter. We gave you a review of Hubble expansion, the distance ladder. We told you what we know about dark matter and the evidence for dark matter. Now we're going to talk about galactic collisions. So here's a map of the local, as I showed you with that image just a little while ago. Um, if you look here, the Milky Way galaxy is like there, and this is to scale. These other galaxies are only a factor of 10 apart versus stars, like I said, are a factor of 10 million apart. And so galaxies are very, very close, and
Looking deep
galaxies collide all the time. In fact, the evolution of galaxies is due to those collisions.
is looking back, back to when the universe was younger. Right now, our best tool for viewing the young universe is the Hubble Space Telescope.
This is Hubble's deepest view into space, known as the Hubble Ultra Deep Field. Here, astronomers have found galaxies so far away that their light began its journey to us more than 13 billion years ago.
We're seeing these galaxies as they were when the universe was just 600 million years old.
In human terms, this discovery is comparable to a teenager looking at a 6-month-old baby.
But for these galaxies, the universe was no nursery. It was more like a brutal football game.
The earliest galaxies were small dwarfs, smaller even than the ones Hubble has seen. They grew by colliding and merging with other small galaxies, as shown in this simulation.
Over billions of years, these mergers built up the giant galaxies we see today. Mergers triggered pulses of star formation that created the elements necessary for planets, and ultimately, life. But to see beyond Hubble, to witness the origin and development of galaxies, astronomers need a new tool. This is Hubble's successor, the James Webb Space Telescope, which is now being built.
Its mirror, 2.75 times the size of Hubble's, and instruments are optimized for a part of the spectrum where the most distant galaxies shine, the infrared. Hubble sees infant galaxies.
The James Webb Space Telescope will see newborns.
If it ever gets launched. It's supposed to be launched this calendar year. Yeah, I'll believe it when I see it. Okay, and here's another simulation. Oops, shoot. Here's another simulation of these colliding galaxies. And this is, so this happened very frequently in the early stages of the universe, and it still happens today. And I'll show you the evidence for that happening to the Milky Way galaxy. And what I'm going to show you is relatively new data. It's only a couple years old that shows we have evidence for at least 47 earlier collisions with the Milky Way galaxy. Yeah. So Nick, I do. So the Hubble was delayed somewhat by, I'm sorry, the James Webb was delayed somewhat by the pandemic, but it's just a mind-blowingly complex instrument. And the thing that scares me is that they've sunk tens of billions of dollars into this. It's sucked up most of NASA's science budget. And it's going to be put in an orbit where it's completely unrepairable. No human can ever reach it because it's going to be very far from the Earth. And so this is a one shot. I mean, so much is riding on that launch. It's really scary. And the unfolding of the James Webb is fraught with peril. I mean, all of us are just going to be holding our teeth. And the fact that it's optimized for infrared is going to be great because that means we can see to the earliest parts of the creation of the universe. But I mean, geez, it's just the most complex instrument ever created by man, and it's just rife full of risk. So, so Nick, it's being placed in a much higher orbit because it's an infrared telescope. If you get too close to the Earth, just the infrared radiation from the heat of the Earth itself swamps the instrument. And I know it does have all those heat shields, but even with those heat shields, the Earth is just way too bright, and it would blast it every time it goes around every 93 minutes, and that was a real limitation of the Hubble, and the reason. But the Hubble was a visible light instrument. This is infrared, and you really can't put an infrared instrument in low Earth orbit. So colliding and emerging galaxies, collisions and mergers dominate the history of large galaxies. And we believe, and this is just a theory, that when you have two spiral galaxies collide that have angular momentums that are opposite to each other, when they collide and the angular momentum essentially goes to zero, what's left over is an elliptical galaxy. If you have two galaxies collide that don't have essentially opposite angular momentum, in other words, the resulting still has a lot of angular momentum, then you're just going to get a larger spiral galaxy. So the current theory is that elliptical galaxies are created by colliding spiral galaxies, that spiral galaxies are fundamental in some sense, and ellipticals are the end result for some of those collisions, not all of them. For collisions where the angular momentum of the result of the collision is much reduced because you have one galaxy rotating one way, one galaxy rotating the other way, and when you hit, you just stop run this experiment. You and your friend sit there and spin around on your roller skates, and you spin in opposite directions, and then you grab each other. What happens is all that spin will just disappear because you've got spin and anti-spin, and they collide and go to zero. Alternatively, if both of you are spinning in the same direction, then when you collide, you're just going to spin around each other very fast. And so here we have, when galaxies collide, lots of strange things happen, and I'll show you those in some videos. And there's lots of consequences of those collisions and mergers. One consequence certainly is we see a spark in star formation because we have these big balls of gas and dust that slam into each other, producing huge shock waves. And those shock waves will collapse the gas and dust cloud and produce stars by the million. And that's why we see bursts of star formation. We call them starburst galaxies. It may also spark black hole activity in the center of these galaxies. Remember, we believe that essentially all galaxies have a supermassive black hole at the center. If we throw a bunch of gas and dust towards that central black hole, what you're going to see is that black hole is going to all of a sudden start generating a lot of activity, a lot of outflow, and a huge spike in luminosity. And we believe that's the genesis of what we call active galactic nuclei, AGNs, which we'll be talking about in a future lecture. Okay. And here is the evidence for the Milky Way colliding with multiple galaxies. And what you see here is a series of colored lines. These colored lines represent stars that seem to be similar to each other in composition and in their velocities. And we believe that those lines are fossils from other galaxies that had previously collided with the Milky Way galaxy. And there's dozens of these lines, which imply that the Milky Way galaxy has collided dozens of times with other galaxies. Some of those galaxies might have been spun off into intergalactic space. Others just coalesced with the Milky Way galaxy and became the Milky Way galaxy itself. We've also discovered these huge streams that spiral out much larger than the Milky Way galaxy. And these huge streams, again, are the result, are the remnants of these collisions of galaxies. And we'll show you some of those, again, more of these simulations. This will be more detailed and slowly. Two galaxies colliding, and you can see as the two spiral galaxies collide, we see all the blue, that's the star formation. And the blue, of course, are the really big OB stars that are so bright. And now you can see that there were two nuclei, but then those two nuclei combined. And now these galaxies slam into each other again, produce another burst of star formation. The nice thing about these simulations, they just use Newtonian gravity. And to make these simulations, all you need is really, really big computers that you can follow a lot of these particles. So this collision took 1 billion years. And we can see with the next image, these are photographs of stars in the process of colliding. And you can see there's, 100 billion to a trillion stars in the Milky Way galaxy. There's 100 billion to a trillion galaxies in the observable universe. And because there's so many, we see so many collisions of these galaxies. We actually see the collisions in the process of colliding. And the next video I'm going to show you is spectacular because what you're going to see is a simulation of collisions of two galaxies, comparing it to some of the images of the galactic collisions we've seen in the sky. So here's two galaxies in the simulation, two spiral galaxies coming in kind of angled. This is a photograph of two galaxies about to collide. Now the two spiral galaxies slam into each other. And you can see it's kind of warping the core of them. This is a photograph of two galaxies colliding. The collision continues, and now we see this kind of a mess, which maps exactly another photograph. And yet another photograph. It's a photograph of two galaxies colliding again. And so here you see, this is the central part of the galaxy, and these are these tidal streams that we showed you in the previous slide around the Milky Way galaxy. So there absolutely is no doubt that galaxies evolve through collisions. They are so relatively close to each other, they slam into each other all the time. And so here I'm coming back to the slide we showed you last time, where in the early part of, it says distant galaxies, so this would be early in the universe, most of the galaxies were peculiar. They're just, different shapes. But if we look at local galaxies, the vast majority are spiral galaxies. And that's because these little guys slammed into each other, they merge, and eventually they create the spiral galaxies. And we have a small number of these where if they collide and they kill most of their angular momentum, they will become not a spiral, but an elliptical galaxy. Okay. Do those tidal arms eventually fly off? Yes, they do. Why is it not placed in a lower orbit and raised after diagnostics being run? Oh, yeah. So Nick, that good question. I don't know so Nick is asking about the James Webb. Why isn't the James Webb put into a low Earth orbit to test it out, and then it's boosted to a higher orbit? I don't know, but I can think of two reasons. The first of all is to do a manned mission to an orbiting satellite is non-trivial and would take months of planning. The second is that the James Webb is very fragile, and if you have it open up completely in low Earth orbit and then boost it, it would certainly break apart. And so it can, it's robust when it's packed up in a little tight ball. It's very fragile when it's opened up completely. And so if you open up completely and then boost it, I think that just wouldn't work. Okay, so the last thing I want to cover today is what happens to us, because the Andromeda Galaxy is about 1,000,000 light years away and it's on a collision course. It is going to slam into the Milky Way galaxy in about 4 billion years. And what you're going to see is a simulation of a series of images of that collision from the point of view of the Earth. So this is the way the sky looks like today, certainly not North Carolina, but in really dark skies, there's the Milky Way galaxy, which again represents the edge-on view of the galaxy we're in. That little dot there is the Andromeda Galaxy, the only galaxy you can see with the naked eye, well, other than the large and small Magellan clouds, which aren't really separate galaxies. In 2 billion years, it's going to dominate the night sky. Look how huge it is. 3.5 billion years, it really dominates the night sky. 3.85 billion years, it's starting to slam into the Milky Way galaxy, and you're going to see a lot of activity, okay? And 3.9 billion years, and in 4 billion years, the sky looks completely different. And at 5 billion years, there's no longer a discernible Milky Way galaxy. It's all over the map. Now, in this collision, do you know what happens to us? Anybody? What happens to the Earth? We die. Well, yeah, well, yes, but not because of the collision, interestingly. The correct answer is nothing. Now, our planet will not be around for other reasons because our sun would have gone red supergiant by then. But assuming that our star was still around, nothing would happen to the Earth. Because remember, the galaxies are a factor of 10 to 1 apart from each other. Stars are a factor of 10 million to 100 million to 1 apart from each other. In typical galactic collisions, no stars collide. There's just too much space, okay? No stars collide. So I'm out of time. That's the end of the lecture. I'll open up for questions. Questions in chat or questions in your mic, it's fine. If the universe started at a point and then expanded, does that mean there is an exact center of the universe? So Jacob, no, there isn't a center of the universe. And we actually showed that in a video last lecture, where as the universe expands, every point on the universe looks like it's expanding. You can think of this as you're on the surface of a balloon, and certainly the farther away you are from other parts of the balloon as the balloon is blowing up, it looks like you're the center of the expansion, but that's true for every single location on that balloon. So yeah, there's no center of the expansion. Other questions? And remember, we have an exam exactly 1 week from today. Thanks. How much of a risk does space debris pose to the James Webb Telescope? So that's a really good question. Not much. And the reason why is that most of the really nasty space debris is in low Earth orbit. And the Hubble is way out at, I think it's L2. I don't remember exactly, but 1,000,000 miles from Earth. And there's very little space debris out there. So it's not one of the risks that they're really that concerned about. It is a big risk for the ISS. And that's why the ISS actually has shields that are oriented towards the direction that it's moving. And that's why the ISS has the capability of moving when it's predicted to intersect the orbit of some space debris. Any other questions? If not, this has been a fun lecture, and I'll see you all on Tuesday. And don't forget the exam on Thursday.